Ja.
Achso, ich wollte das.
Okay, then I'd like to welcome all of you to the TCPM session here at this IETF meeting. First of all, for those of you who don't know me, my name is Michael Scharf, and next to me is Michael Tüxen. And with that, I'd like to start today's session with the usual note well. So this is not the first session today, so I assume that all of you know that this is an IETF working group. So everything that's done here is covered by the note well. So please read the note well and please take it into account specifically regarding, for example, IPR declarations. Regarding the logistics, we do need a note taker. We haven't found one in advance, so we will not move forward without a volunteer. So do we have a volunteer for note taking? So if you're interested in any work in this session here, you have to consider volunteering. Okay, we have one. Okay, thanks a lot. I mean, hopefully you use the Etherpad, as I will also, as far as I can, for example, pay attention to the Etherpad, but and maybe you can do this in a collaborative style, but anyway, we do need note-taking. I will monitor myself the Meet Echo, but of course, if something shows up there, we appreciate if somebody else can also relay that. Do we have another volunteer for chapter scribe? Okay, Mirja is doing it. And then last but not least, specifically for the note takers, if you go to the mic, please don't forget to say your name so that we can put your name into the minutes. Regarding the agenda, so this is what has been sent out before the meeting. So our proposal is first, of course, to do the usual status update. Then we have two presentations for working group items. First, Olivier on the converter draft, and then Mirja and Bob on accurate ECN and ECN++. And then we have today quite a couple of other presentations that are not at all about working group items. Actually, most of them are about documents that are not even in this working group, but they are all related to TCPM business. So we thought it's good to have a discussion on those documents here. And last but not least, if we end early, we will have a final presentation on a more researchy talk. Is there any feedback on this agenda? Any agenda bashing? Okay, that's not the case. So then I will move forward with our usual status update. So first of all, we have one recent RFC. It's the alternative backoff. It's only one recent RFC, but we have a couple of documents that are getting closer to completion in the working group. So hopefully in the next meetings, this list will have a couple of more entries. Then I'd like to briefly go through all working group documents. For the first three ones, we will have presentations here, so I will not say too much about them. So we will see a presentation on the converter draft, which has been recently updated. We will have status updates on accurate ECN and briefly on the generalized ECN or ECN++. So I will also postpone the discussion on that one to the actual presentations. Then there was recently quite a bit of discussion on the mailing list on the RTO consideration document, which is good. There was also an update, or I think even more than one update. So there has been progress on that document. And at the moment, the chairs wait for reviews. So we have asked Gori and Jana for reviews of this document. And that is at the moment basically thing we are waiting on. But other than that, we observe that the document is improving, and we will see if we can go to a working group last call relatively soon. Then we have two other documents that unfortunately have expired. The first one, REC, is something that we probably should review what we should do with the document. Maybe we can postpone this discussion to one of the later talks from Praveen. I've seen some comments on REC in his presentation. In any case, having expired working group documents is not a good status for such a document. So hopefully we get resubmissions of this document. For the REC one, definitely we have to have a discussion if that document is in a stable state and if it can move forward. But the first thing for that to happen is that we need an active document. The second document, EDO, has not changed the status recently, so I assume there's still ongoing testing effort on basically the question whether that scheme can be implemented and what are the potential issues with implementation. And then, last but not least, we have the 793 BIS document. This is also a document that has recently been updated, and I've put here on the slide the comment from Wes, who believes that the document is getting into a pretty decent shape. We will not discuss this document in this meeting, but the chairs are discussing with the editor on what to do, possibly in one of the next meetings, as the document is moving forward. And I'd just like to point out that in his last email to the mailing list, Wes has flagged a couple of sections in the most recent version of the document, and he's looking for feedback on those sections. So please have a look at those questions. We do look for feedback, and if you have any thoughts on these technical questions, then please feel free to comment on them. We recently have performed a working group adoption call on the 2140 BIS document. And the working group adoption call has run until Friday last week. So we didn't get a lot of feedback, but there has also been no pushback on working group adoption. So the understanding of the chairs is that there is consensus in the working group to adopt this document. Are there any comments on that? Okay, I see no comments. So the consensus on that document is to adopt it as a TCPM working group item. And then this is my last slide. This is just a heads up on a document that is not in TCPM, but we have repeatedly presented the document here in TCPM, simply because it's quite related to our work here. It's the document on the constraint-out networks. So this document has been presented in detail last meeting, and this has triggered quite a bit of excellent reviews after the last presentation. And also specifically, I'd like to highlight that we got a pretty good list of feedback comments from Stuart. We work on addressing these comments. There will be some technical changes in the document to address all the comments that have been made. And I assume the main author will send a summary of the changes to the list. But other than that, the feedback in general seems positive. So the authors believe that this document is getting pretty close to working group last call. And so that's why I asked the working group to carefully review the most recent version. We will, it's not a TCPM document, but it has been agreed in the past that there will be a joint working group last call in the Lightweight IP working, or Lightweight IG working group and TCPM. So you will see traffic on this on the mailing list. And that is actually the last slide in the chair part. So are there any other open issues on the working group status, anything that we have missed here in the status update? Okay, then I'd like to say thanks, and then we will move on towards the presentations of working group items, and we will start with Olivier. Yes, but you can't
yes. Okay, so let me just give you an update on the 0RTT TCP converter document. Next slide. So just to recall what's the basic design. So the converter protocol is an application level protocol, which means that the server is listening on a specific port, and we are sending commands and responses, and these commands and responses are encoded as type length values. And what's specific about this protocol is that the commands are sent at the beginning of the byte stream, so inside the SYN, and in the SYN plus ACK or in the next packet. And this is a plain mode transport between the client and the converters. And the motivation for this work is to allow a TCP connection to be established through a proxy so that you can learn whether a remote server supports a given TCP option or not. And the main use case is multipass TCP, so that you can get multipass TCP on the access network through the proxy, and then learn whether the final destination supports MPTCP or not. Next slide. Let me just show you how it works. So next slide. So the client sends a SYN to the converter to connect to a specific server, and the converter message is encoded as a TLV in the SYN payload. And the converter will send a SYN to the server. The server will reply. Next slide. And then the converter can confirm, next slide, the establishment of the connection by using a TLV information in the payload to confirm that the connection to the remote server has been established. And then next slide, at this stage, we have a transparent byte stream through the converter between the client and the server in both directions. Next slide. So what are the main changes since the last presentation of this work? We got feedback from different implementers, and they asked to tweak a bit the protocol. One issue was that in the previous draft, we said that the error messages would be encoded inside reset segments, but in practice, there are some stacks that have difficulties in parsing data in reset segments, although it's supported by RFC 793. So we removed that, and there is now an open source client library which is being started. And we also simplified the design. So in the previous version, we relied on TFO, but we know that TFO has issues in some deployment use case. And what we did is that instead of using the TFO option to encode a cookie to secure the connection between the client and the server, we moved the cookie to the user space by using a specific TLV. So the same functionality is there, but it's not using TCP options anymore. Next slide. So let me show you how the cookie works. So the client sends the SYN with the connect message to the converter. The converter there is no cookie inside the SYN. And so what the converter will do is that it will compute a cookie, And the way to compute a cookie could be like we do compute the cookies in TFO. So by using the hash of the IP source address, then you can return the cookie in the SYN+ACK with an error message that indicates the cookie that the client should use. And then next slide, so we can restart the connection. Again, a SYN, we encode the cookie that was returned by the converter. Now the converter can check the cookie by doing again a hash computation, for example, but there are other possibilities. And then the cookie, next slide, can establish the SYN, and then next slide you get the response from the server. And next slide you get the SYN+ACK, and the connection is established as before. Next slide. Then there are also use cases where the client would send the cookie. Next slide. So you send a SYN with an invalid cookie, and this can be checked by the converter. And the converter can return an error message saying that this cookie was not authorized because, for example, the cookie has expired on the converter, and the converter wants to get a new cookie from the client to re-authenticate that the client owns the IP address from which it received the SYN. So it's exactly the same stuff as what we do in TFO by using TCP options, except that you do that inside the payload, so we can have cookies that are much larger than the ones that we use in the TFO option. The main use case for this converter draft is to support multipass TCP in access network. So typically what you would have, so you would have a smartphone that uses multipass TCP. Next slide. So you can send a SYN with the MP capable option and different options. In the example, I only show the MSS option, but there are other options. So you send the connect, then it goes to the server. The server returns back the SYN+ACK, and then what the converter does is that it will return in the SYN+ACK the MP capable option to confirm that it's using MP TCP between the smartphone and the converter, and it also provides to the client the TCP options that have been returned by the remote server, so that the client can learn with that information that the final server does not support multipass TCP. And so if the client wants to use the multipass capabilities on the access network, then it should use a converter. On the next slide, we will see what happens when the server supports multipass TCP. Next slide. So again, we send the SYN. Next slide, we send it to the server. The server, next slide, replies with the MP capable option. And then the converter will return in the extended TCP header TLV the MP capable option that was returned by the server. And so the client now knows that to reach this specific server, it can use multipass TCP. And so for the next TCP connections, it can send a SYN directly to the final server without using the proxy. So that's a way to learn whether to be able to use MPTCP on the access network through the converter when the server does not support multipass TCP. And when the server supports multipass TCP, you can learn it and use direct connection to the server. Next slide. So to summarize what happened, so we believe that now we have a simplified design which takes into account all the feedbacks we receive from implementers and on the mailing list. There is ongoing work in different standardization about using this convert protocol, and it's being adopted by two standardization bodies. So one is the Broadband Forum, which uses that as one of the solutions for hybrid access network based on multipass TCP, and this is WT378, which is now whose approbation is being finalized. And it's also used by 3GPP for the ATSS service, which will allow to combine 5G and Wi-Fi, but also other types of network. And this is part of the work in 23701, and there was a discussion during last year in 23973 that explain why 3GPP has selected multipass TCP and the convert protocol for the ATSS service. And the authors believe that with that, the document is ready to go for working group last call and then to progress.
So are there any comments on this document?
Praveen, Microsoft. I'm very curious why you decided to not use TCP fast open, because fast open does have an option where the cookie size can be 0. If the server doesn't care about enforcing security, the cookie size can be 0. And the advantage of using fast open is that most operating systems, at least on the client side, would already support sending data in the SYN for you. So otherwise, you're looking at like using raw sockets or something to do this.
So we have a specific protocol. And we want to be able to confirm that the SYN comes from a client that we know can receive SYN plus ACK. So for that, we need to have a cookie. And the cookie, there are two ways to encode it. One is to encode it in the TCP header as a TCP option, or we can encode it in the payload. We believe that it's easier to encode it in the payload because we have less restriction in terms of space.
Oh.
And if you put a TFO option which contains a zero-length cookie and then you put the cookie inside the payload, there is no real benefit of having a TFO option which has a zero length.
The benefit is that there is an API which allows you to do this without using raw sockets. Otherwise, you're not going to be able to do this on most operating systems.
Oh, no, there are other ways than using raw sockets in different implementations.
No, I understand, but I'm saying that using the TFO API is probably the cleanest way to do this.
Yes, but you can use the TFO API without using the TFO option. That's orthogonal.
Yeah, just one addition to the comment about the support of the zero cookie in the for TCP/4. So we used to have that in previous version of the specification since version 04, but we have a discussion with other implementers, vendors, and they see that at least for their user equipment, it's really difficult to have the TFO supported directly as an option. And this is why we have started with Olivier to redesign and to provide the same functionality using the TLV instead of the TFO. So we used to have that, but given the feedback we received from the other implementers, there's only one vendor who says that they support TFO as a TCP option, but for the others, they told us that they have more difficulty to support it.
I would be very curious on what kind of middlebox issues you see when you include data in the SYN without the TFO option, because you're going to see two patterns of traffic on the network now, where one has the TFO option and the data, and one where there is no option and there's going to be data. So it just seems to me that TFO is the cleaner approach, but yeah.
Yeah, we have not yet tested that in a real network with middle boxes, but I think the deployment use case that are mentioned on the last slide, there are use cases where the network operator will control the path, and so we know that there is no middle box that will mess up. And whether we have a middle box that messes up with having TCP data in the payload or having a TFO option, I think it's the same problem. And I don't see a difference.
So that part I agree. I think there are already problems with middle boxes, even so you have the option. But I think having the option is a much cleaner design approach here if you're talking about an application protocol, because otherwise you change the semantics of TCP, the underlying transport. But I also need to look at the draft in detail because I don't think you rule it out completely. So it depends probably on the exact phrasing in the draft, what makes sense.
But so TFO was inserted in TCP to support web applications and to have a way to support the establishment of SYN, of data in the SYN in applications that cannot encode the cookie information in the application itself. So we are here in a different situation. So we have an application that can support the cookie inside the application itself. And I think it's cleaner to put the cookie information inside the application.
So that's fine. But from an architectural point of view, just saying I want suddenly data on the SYN is a change to the TCP protocol, right? And the only way we support this is like using TFO.
If the consensus is that we should have a TFO option of zero length and then encode the cookie inside the payload, because there we could have a longer cookies, then I'm fine with that as well. If it's the consensus, then we can do that. We can live with that as well.
So I think that would be the clean design approach to go for. And then maybe you want to have a section saying if you're in a controlled environment and you know everything is like this, you might also do it without the option. But cleaner it would be using the option.
So you would suggest the TFO option with zero length? Then it's fine for me. I would just lose a few bytes in the header, but this is fine.
Christoph Barsch, Apple. I want to address the comment about the mailbox issues when using TFO without the TFO option. Independent from the converter, we have done experiments, and it actually is it's not much better, but it's better than with the option. So you can use SYN with data and have more roughly 10% higher success rate.
Sure, that's interesting data, but I do think like the way we have documented usage of SYN and data is with the TF option. I do think that's cleaner on the network, because otherwise now you're going to have cases where there's two types of network patterns appearing on the internet, which is harder for everybody to deal with.
Then maybe, isn't RFC 7413 also saying that one could use TFO without the option?
So this is Michael speaking as chair. So then we have here on this slide a very unusual thing that other SDOs directly reference our work. So my question to the authors is, can you, or maybe to other people in the room, can you share more details on how this spec is used by Prop and Forum or 3GPP? And the specific question that I'd like to raise is if there is an issue that this is experimental work, because we made a call some time ago that this is an experimental protocol. And I don't know whether that is an issue for other SDOs. So if you have some insights on that, that would be useful information to us.
Yeah. So as information for the first question that you asked about the current integration in the 3GPP specification. So far, the converter specification is the only specification which is used for the aggregation there. So they are relying exclusively on the solution we are developing here in the TCPM working group for their work. And they have some time constraint in the finalizing the specification. So they are waiting for us to finalize the RFC here. So if we can finalize it by during this year, this will be really be great for their work, because there is I would say it's only editorial notes there that they say that we need the RFC staff to be published numbers so that we have the work integrated. So this is for your first question. For the second one about the experimental and for standard track, just for the record, when we started this work, we have done that in the MPTCP working group, and at that time the MPTCP specification is experimental, so we left that header there as experimental level there. So for us, we are open here. If there is no extra delay in the development of the specification, I would personally be in favor to consider this work as a candidate for standard track. But if this will induce, I would say, additional discussions and in terms of more long time to have the specification finalized, we can go with the experimental and then see the feedback from the field and the deployment, and then we come back here to the IETF to promote the spec. So my favorite option is to go for the standard track if it's possible. If not, we can maintain the current track.
Mia Kulevin, SAD, we coordinate this with 3GP, and we're both sides are aware of this dependency. We just had a meeting about it actually, and usually it's not a problem to have an experimental reference there. Okay,
so just for the chair's information, can we please have a show of hands how many have read specifically the last version of this document, because there were some changes in there. So this is about between 5 and 10. So my understanding of the feedback is that we do need an update of the document. But other than that, we are hearing that this document is moving forward, and there seems to be both ongoing implementation effort as well as use in other SDOs. So that's a good sign. So from a chair perspective, we would head for working group last call relatively soon. So that's why we clearly need an update here, but after we see the update, we will definitely analyze whether we can go for working group last call. So please pay attention, and we might run the working group last call even prior to the next meeting. Okay.
Fine. Thank you.
Then we move on to the next topic, which is also about working group documents. That is accurate ECN and ECN++. And I think Mirja is presenting.
Okay, hello, I'm Mia Kulevint. My co-authors are Bob and Richard, who are here as well today. This is a quick update, and I hope we're done with this document. So first, a quick recap. What was the problem that we're solving here? The problem is ECN is there. ECN is around for a while. And there is feedback from the receiver to the sender to tell if there were any markings seen on the path. And then the receiver is required to, or should be, reacting to it with some kind of congestion reaction. So to provide this feedback, there are already 3 bits in the TCP header, but the feedback itself is limited to just like providing 1 signal per round trip time. So you don't know with the classic ECN approach how many markings have there been. Has it been like a severe congestion or just like a very light congestion? And if you have this information, however, you can adapt your congestion control to this information, make it more reactable. Next slide. So what accurate ECN does, it reuses those 3 bits and provides more accurate information to the sender. So these 3 bits after negotiation are a field which have a counter and provides a number of markings that were observed, congestion markings. And in addition, we also have a TCP option that can provide even more accurate information about the number of bytes that were marked with like one or the other marking. The option is completely optional because it may not pass middle boxes or you just may not need it. Next. Yeah, so this is already kind of was addressed the last time, I think, already. There were a main question about what if this experiment fails? We have then like burned all the heads, all the bits in the header for the negotiation. So we make sure that all unused combinations still lead to some kind of accurate ECN negotiations. So we have a way open to further extend and update the accurate ECN specification in future. Do you want to interrupt now?
Yeah, I'd like to at least make the working. I'm Michael speaking from the floor. So indeed we have discussed this question quite a bit. To me, what is presented here is forward compatibility makes a lot of sense if you're sure that accurate ECN is the right thing to do forever, but it's experimental. So we don't know what the experiment outcome will be, and in specifically the last sentence, so that we make the behavior of accurate ECN predictable for future protocols, that assumes to me that the future protocol is accurate ECN. And as individual contributor, I personally could foresee a world where the accurate ECN experiment fails, and we will do something else. And then, to me, this specific rule doesn't help at all. I don't mind at the end of the day, but to me, as I said, to me, for an experiment, what is said here is we are speculating here that the accurate ECN experiment will succeed, and I'm not sure if that will be true based on what I know myself, but I might be wrong.
Do you want to speak to that? Or yeah, Bob Briscoe. Yeah, that last sentence, which I wrote, I obviously didn't write it in a way that Michael would not find it ambiguous, because I meant to say for future ECN feedback protocols. In other words, if this fails, what do existing accurate ECN servers do? They've got, one of 3 choices. Do they do not ECN, 3168 ECN, or what they currently, what they've been coded to do, which is accurate ECN? When a client talks to only to an accurate ECN server, this isn't to, any other server. It's what should an accurate ECN server do if it gets a field that currently doesn't exist, a value that currently doesn't exist. That's all this question's asking.
Gori Fairhurst, as TSVWG chair, co-chair. This document is kind of related to the L4S environment, and it runs an experiment, and L4S is an experiment. So I'm just kind of calling out that there are now 2 experiments which have some sort of dependency on each other. Maybe this is necessary to have some form of ECN feedback for L4S to work, so I understand this. I'm just asking for a comfort level amongst the editors and maybe amongst other people, saying that there are two experiments here.
Just to clarify one point, like there is a dependency from L4S on accurate ECN, but not the other way around.
Indeed, that's why I came as TSVWG chair here to say, you know, we have a set of documents that depend upon this, or something similar. And did anybody come to the mic and scream? If they have opinions, then they should talk to David and I, who are here at the IETF, and tell us if they're concerned about running these two experiments in parallel.
Okay. In the recent version, we also updated based on a discussion from last time, which was triggered by Praveen mainly, and we tried to clarify that the option is really optional, and that also means in your depending use case, you might have benefits in not even implementing it because that can optimize your code. So we did change the wording a little bit to hopefully make this clear now. I mean, yeah. This is the wording, or check the draft. Next slide. And then the other discussion was triggered by Yu Chung, who was favoring the DCTCP style feedback over the feedback we're providing right now. We had a lot of discussion about it, and part of the problem is that the design we provide right now is probably more optimized for an internet scenario where you expect like a low number of congestion markings, while in a data center scenario you might have a high number of congestion markings, and therefore in some cases the data center TCP feedback might be more optimal. However, the optimization really depends on the offloading you're implementing. And there is a way to also optimize the offloading for accurate TCN. So we talk a little bit more about this in the draft. But more importantly is also that there was at the hackathon, there were people working on the accurate ECN patch and trying to get this in the kernel, and at the same time also working on offloading. And the problems we see with offloading, we believe, are mostly historical. We don't even know how this got into the kernel. So they're trying to fix that and provide patches for that as well. Yeah, and that's kind of halfway what I already said. Oliver Tillmans is working based on like my original type proof of concept implementation. He's basically implementing it completely, which is great. And he's bringing this into the kernel. And the first step will actually bring it into the kernel without the option to really minimize the changes you have to do in the kernel. And then later on provide another patch to have the option part as a compile option if you want to use it. So that's ongoing. I don't think the patch or the request for comments landed yet, but should be this week probably. Yeah, so in this case, I think actually we have addressed all comments. This draft has been around for a long while. We heard that there's a dependency to a different working group, so we really hope that we can move forward.
Okay, so are there any further comments, first of all? As we've seen here and specifically on the last slide, quite a bit on comments that are actually about implementation details, such as GRO. So that's why I wonder specifically to the implementers in this room. Do you have any further comments on the most recent version of the protocol? Or do you feel comfortable with moving this forward? So I'm specifically asking people who own implementations in the room.
Hi, Bob Briscoe. Praveen, myself, and a couple of other people are planning to get together to talk about this GRO issue this week. So if anyone wants to talk about it, get in touch and we'll maybe put where we're going on the list. Yeah. Okay.
Yeah, anyway, I mean, I'm seeing here on this slide that we probably will get a document update in any case. So if there are any open issues, then we will probably see it in the next version anyway. So maybe, can you give me a show of hands how many of you have read the latest version or one of the earlier versions of this document? So to the note taker, this is of the order of 10 people. And specifically among those who have read the document, is there anybody who has concerns in starting a working group last call relatively soon, as I say, after we've seen the next update addressing the minor remaining things? So this would be an excellent opportunity to speak up. Okay, so for the note taker, so we have no concerns regarding starting a working group last call. So regarding the next step, so first of all, I think we are waiting for an update, even if it's small editorial things. So that's definitely something that should be done. And then the chairs will check if we can start a working group last call. We can do this in that case anyway on the list, so that doesn't have to wait for the next meeting.
Yes, please. Thanks.
Okay, and with that we have finished the working group items, so we move on to the individual working documents here, and I will start myself. So now speaking from the presenter line, and I'd like to present a new document that has not been presented in TCPM before. And it basically raises the question whether we have to start working on a Yang module for TCP. So next slide, please. So the background of this work is mostly TCP implementations on embedded devices. So that is something that in TCPM we actually hardly discuss because we focus a lot on the TCP stacks that run on hosts. Nonetheless, obviously on a modern embedded device, such as a router, for example, there's obviously a TCP stack and a big number of control and management plane protocols that run TCP, including BGP and, for example, network management protocols. And that means we do have TCP stacks on those devices. And for those of you who happen to visit other areas in the IETF, you probably have seen that there is a lot of work in other areas, in other working groups in the IETF, given by the fact that the management of devices moves from SNMP to netconf Yang. That is something that has triggered a lot of work in the IETF outside transport area. But there's one specific issue that now matters possibly to this working group, namely the fact that we do have a TCP MIP, so it's standardized in RFC 4022. And I tried to figure out who has implemented that. So I found data sheets of at least 3 different devices from different vendors claiming that they have an implementation of that MIP. Now the IETF has decided to deprecate MIPs more or less, or at least to move to netconf Yang as a superior technology. And that now raises the question, so what happens with the management of TCP stacks on devices that will, maybe at the moment they are still managed by SNMP, but the management move is to netconf Yang. There is one candidate solution for devices that have used the MIP. There is a way to translate a MIP to a Yang module. So there's an algorithm to do that. And in fact, I have found signs that vendors might even do that. But of course, that is a translation of a pretty old MIP. And if you check the details of that MIP, then you will see that it's a pretty old RFC actually. Which brings up the question if this is indeed the right thing to do. And that's specifically the question that I'd like to raise here. And I want to put up a disclaimer right from the beginning. So this talk is really about devices that are managed by network management protocols such as netconf-yang or resconf-yang. I'm not necessarily speaking about an end host operating system here, because you know very well that there are other means to configure a TCP stack. So I'm talking here about devices that are natively managed by Yang modules. In order to analyze a little bit more in detail what we have right now there, I've put on the next slide the content of the TCP MIP, but I decided not to use the MIP itself, but instead to convert it to a Yang module. I'm not saying that this is a reasonable thing to do, but it at least gives an overview of what the TCP MIP originally has standardized, and it also provides a potential solution how a Yang model could hypothetically look like if we decided to standardize a Yang module for TCP. You can see this auto-generated Yang model here, or more specifically the tree version out of it. So this is there's no editing here. It's a fully automatic conversion of the TCP MIP. And if you're a little bit familiar with the tree structure of Yang modules, you can see here the key pieces that we have in this Yang module. So the first important point to note is that most information in the TCP MIP is read-only. So actually it's mostly a MIP for monitoring. There is hardly any configuration in that MIP except for one detail. Also, if you go to the lower part of this slide, you can see there's one read-write attribute in the table there. This is supposed to be a means to reset the TCP connection by resetting one of the table entries. But in general, it's a read-only MIP, and it contains more or less 4 different sorts of entries. First, there is a little bit of information about the TCP configuration, but it's limited to the configuration of the retransmission timeout, most notably about the minimum timeout. And if you look more in detail what is actually in the MIP, it's a pretty outdated, they're pretty outdated references to TCP specs there. Second, the MIP includes a number of stat counters, for example, on connection statistics. And then there are 2 tables. There's a connection table that basically lists the active connections of that device, and there's a TCP listener table. And that's basically what the MIP is all about. So we see it's a pretty simple MIP after all, and that is probably also one of the reasons why it might have been implemented, since it's a relatively simple model. And that obviously brings us to the question on the next slide. So is this something that we have to care about? And I have started this document mostly as a placeholder. So I will not argue that this is something that can be adapted at that point in time. But still, if we look at what happens in other working groups, how much effort is spent on designing Yang modules. So to me, there is a question in the room whether we need something in that space. That is, whether it makes sense to more seriously start working on a Yang module for TCP, specifically as a successor of the MIP. I would note 2 observations. So first of all, I believe that this work would be in scope of the TCP/M charter, because we have a wording in there that talks about interfaces that maintain TCP utilities. This is the network management interface. So I believe if we decided to do something in the longer run, it would be in the charter. And second, other IETF work in that space is typically standards track, which is, we have a pretty high bar here in TCP/M on standards track. And with that, I think we have a question.
Michael Abramson, it's less of a question and more of a statement, actually. So we're using netconf and Yang to manage everything. We're trying to move in that direction. We're administrating servers, home routers, core routers, whatever. Most of these things actually speak TCP. I would like a comprehensive Yang model. So please do not just auto-translate whatever we had lying in the cupboard, but a comprehensive work on typical settings that is available on devices.
Okay, that's a fair point. I mean, one of the things that what I could offer is that I would try to reach out to vendors in that space, because this is something obviously where we need input from vendors on what this set of typical things is. Of course, we know that there are a couple of parameters that are pretty common for TCP configuration that are probably uniform, but obviously that is something where typically as a vendor input would be highly appreciated. But as I said, one of the potential next steps, what I could offer is that I reach out to people asking for input on that, and then we can see if there's a chance, for example, to agree on such a set of parameters.
Yes, that is always the hard part. But for instance, all the settings in the Linux kernel I can set using sysctl or /proc. That would be something I would like to see in this model, that when it's related to TCP, that's.
Lars Eckert. So I remember when we did the MIPS, right? Because that was the cool thing that everybody needed to manage their networks. And it was super painful because nobody actually cared. And eStats was even more painful than the basic MIP, right? And so unless there was like a line of operators out the room that scream for this, I would not want to do this, simply because it's going to be very, very painful and very, very hard. And, you know, yeah, you can say I want everything that's in Linux, that's knobs, but that's Linux. What about other operating systems, right? There's almost no commonality, even when you have TCP info between the different stacks, right? And a MIP or a YANG model is all about that level of abstraction. It's exactly what made the MIP hard, and it's going to be exactly what makes this hard. So I would not want to do this unless somebody's really, 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 really committed to doing this and getting like a bunch of operators that are and others on board.
Well, that is maybe not the challenge. Maybe somebody has volunteered to do the painful work. The question is if there are others that want to share that pain.
So it's going to be pain for the group for a long time, like it was for MIBS, and I don't want to share that pain.
So I think that we can find a balance. This work, I think this is something which is really interesting, and this is something that can be useful. It is useful because if we see some simple existing YANG models, we will say that they are touching on TCP stuff. Take, for example, the BGP ongoing YANG model. You will see that they are defining some generic TCP parameters there. So what personally I would like to see, if you have something here in TCPM, to see that these are, I would say, our first lower bar in terms of the generic parameters that we can use to tune the TCP stack, for instance, MSS, this kind of stuff, and so on. So these modules can reuse what you can define here at generic, I would say, parameters for configuring TCPM. So I provided the example of BGP YANG model, but you can find other models in which they are touching exactly on the same stuff. So instead of having something which is spread among a list of YANG model, I prefer to have something which is really, I would say, the reference, not have everything as mentioned by Mikael, because I think this one it will be really painful to have something which is really comprehensive from day one. Just start with something which is really, I would say, balanced, and then take the work from there. I support this work. Thank you for doing that.
Michael Abramson again. Yeah, of course, I'll take less if I actually get anything. I mean, this is not an all or nothing proposition. And I know very few people who the best thing that they know is to create a YANG model for management. This has never been a sexy thing. Very few people enjoy it. It's painful. Okay, I'll give you that. But there must be a bunch of basic functionality that most TCP stacks share. I don't know. I've turned on SYN cookies in a bunch of different operating systems and so on. I mean, there must be at least 30, 50 parameters that is very common. So we can start there. That's a perfect first delivery. Just the knobs that are typically there in most operating systems. And we can augment later. So it doesn't have to be perfect from day one. And it's better to deliver something in 6 months and then another thing in a year, more enhancement in a year. Just keep the pipeline going than to get it to sit on it for 4 years until we think it's perfect.
Yeah, so just to be clear, I don't believe that we can ever come up with a entirely comprehensive model. So because, I mean, TCP stacks do differ. What is possibly doable is to do the basic knobs that directly map to specs. So there are a couple of things where we have an RFC that basically specifies that there is something that's optional that can be turned on and off. And that is something that we can see how common that is among different implementations. This will still, in my opinion, not be a comprehensive configuration because implementations do things beyond that, but this is something that's perfectly suited for augmentation then.
Yes, comprehensive is always subjective, and I'd rather take less than nothing. So I would like comprehensive, but if I can't get that, I would like as much as possible.
Lars, yeah, I want a pony. So this is going to be the same thing we did with the MIP model, right? It's going to get super complicated very quickly, even with SYN cookies. But even like something very simple, it changes from kernel version to kernel version, potentially, right? It changes from operating system to operating system. Multiply this with all the different options and parameters we have. This is and given that we don't have one now, and we don't seem to have huge operational problems, I really don't think we need to do this. And I don't know why the working group needs to do this, given how very, very painful it was for MIPS, that everybody wanted and then nobody used it.
Well, that's not true. I mean, as I said, I found at least 3 implementations. So there are implementations, not in the Linux kernel, of course.
So Philip Teasel, I'm looking at this at the moment from the tabs perspective, and we will soon have for tabs to define some way to set TCP specific options. And I think having a Yang model to import there and just say, okay, this is the list of properties we can import into tabs and say, these are the TCP specific options would be really, really cool. So, but I'm only seeing me from a consumer of that model and not as the one who is doing the hardware, sorry.
Michael Dixon from the floor. The step stuff, isn't that connection specific? So aren't you talking about parameters you want to set on per transport connection thing? Because some of the stuff we are talking there is about his system-wide settings.
It is connection specific, but I think going to that direction could also be interesting to see which of the settings of this Yang model can be applied on a per connection basis, and which can only be set as a system default. So I think these are 2 different kinds of settings on different branches of a tree, which might make sense to say, okay, these are connection specific settings, and these are settings that are globally for the system.
This makes the game more complex. So I think a lot of implementations have the capability to tune several TCP parameters system-wide, but if it comes to socket options, it's much more diverse and less stable. I mean, socket options come much faster than syscontrols.
Okay, so as I said before, I mean, at the moment this is a placeholder, so we don't have to come to a conclusion in this meeting. So technically, I think we can decide to do at least 4 things here in this working group. The first thing is what Lars has just suggested, to do nothing. The other 2 options here I've also discussed. We could either do a Yang module that's relatively basic, similar to the MIP, probably mostly read-only, or we can try to do something more comprehensive. And of course, I totally agree, it's easy to do to boil the ocean in Yang models, so it can get painful. We all know that. My proposal is, I would volunteer to have a second talk on that maybe in the next IETF meeting with some additional insight on my side. So that would be my offer to this working group, but if the working group believes that we should stop this activity just right now, then I will also be fine. So that is, in particular, if you believe that I should not invest any further cycles on that, so it would be perfect to say that now.
Bob, you want to say something?
Yeah, not about this though. I just wanted to get in before the next talk.
Okay. So I think it's still an individual contribution, so you can do whatever you want.
Sure.
But I got, the feedback I got, or the impression I got is, if you can reach out to operators and figure out if there is a need for using this stuff, then it might help us to address the concerns raised by Lars. I mean, we had positive and negative, and if we can figure out if we will have consumers of this work, then we might make a positive decision. Then I would say thank you, and it's an intro by Bob.
Yeah. At the end of Mia's talk, there was one slide that was an announcement about the other working group draft I'm working on, which is the ECN++ one, and a bit of miscommunication. I asked if you could just have a minute on it between slots.
We have to just come here. Sorry about that. You have to open the accurate ECN one. Okay.
Yeah, the accurate ECN, and it's the last slide.
Yeah, sorry about that. Indeed, there was a miscommunication. No, the next one. There's the second one.
So it's about this draft.
That's why we're on time.
No, there's only one more slide, just as if you can move on to the next one. The last Singapore, I guess it was, talked a lot about this problem where this whole draft seemed to be completely destroyed because we discovered 84% of servers around the world turn off ECN if you set ECT on the SIN. Since worked out a solution, written the patch, it's gone into the Linux mainline pipeline. There's been some feedback and come out and gone back in again, but basically we've worked out a way so that when you set ECT on the SIN, if you're using accurate ECN or any future protocol that might replace it, the test that turns off ECN won't happen. It will only happen if it's an old ECN setup SIN. So that's just a one-line change, and so we're hoping that will get backported as far back as possible, as quickly as possible, get auto-updated, and a lot of the problem will go away, but we'll see how much when we measure it in a couple of years' time, maybe. Okay.
Any comments? If not, then we are up to DNS.
So thanks, I'm Dwayne Wessels. This is a presentation about a draft with co-author John Christoph. I'd like to thank the chairs for inviting me to come and present this. This is work that's really in the DNSOP working group. So I don't normally participate in TCPM, but I hope you find this at least a little bit interesting. Here's the abstract from the draft, and it talks about how this is a document that's about encouraging operators to permit DNS over TCP and describe some of the problems that can be encountered if that is not done. Next, please. So a little bit of how we got to this point. Going back to RFC 1123, it talks about DNS. It talks about UDP and TCP. It says, servers, resolvers, and servers must support UDP and should support TCP for non-zone transfer queries. A later RFC says that UDP is the preferred protocol, although TCP is used for zone transfers. So after this point in time, it sort of became folklore that most DNS occurs over UDP, and TCP is really only used for zone transfers, and we find cases where it's blocked in firewalls, where you would not expect zone transfers to occur, things like that. In the late 1990s, DNS started having things happen to it like DNSSEC and eDNS0. And in 2010, RFC 5966 starts to address these misconceptions that have cropped up over time. But this RFC goes a little bit unnoticed and really kind of didn't go far enough. So next slide. So the reality is when in DNS, if you have to deal with large responses, sort of bigger than MTU size, your choice is either to fragment or to truncate. And we see problems in both cases. Fragments are sometimes blocked by firewalls, and if you truncate, then it leads to TCP, and TCP over DNS is also sometimes blocked by firewalls, and of course it adds latency and so on. So the situation that we're in now is that DNS clients have a lot of complex retry logic to try to work through all these problems. They'll do things like retrying their queries with different eDNS buffer sizes to try to find the point at which their queries are able to succeed. Next, please. So RFC 7766 was written to update the older 5966. This is an RFC that's all about implementation requirements for DNS over TCP. It does not make any recommendations to operators, but it talks about the things listed here. It talks about how all implementations must support UDP and TCP. It says that resolvers or clients may elect to use TCP first without trying UDP. It recommends and to keep idle connections open for the order of seconds, whereas the older RFC said 2 minutes. It says that servers can impose limits on the number of TCP connections, and it advises clients to be prepared to handle out-of-order responses. Next, please. So this draft that we're talking about today is sort of a companion to that, whereas the other one is about implementation requirements. This one is about operational requirements. And the idea is to encourage operators to be aware of these issues and ensure that DNS over TCP is handled equivalently as it is in UDP. So it says a lot of these bullets here are just cut and pasted from the draft. It says authoritative servers must service TCP queries for these reasons, and recursive servers must service TCP queries for similar reasons. Talks about name servers may need to limit resources devoted to TCP, but must not refuse to service a query just because it would have succeeded over some other transport protocol. And it has a lot to say about how filtering of DNS over TCP is harmful in general case, while still recognizing that there may be local policy cases where you would need to do some of that kind of filtering. And it says that network operators must allow DNS service over both UDP and TCP. So getting into a little bit more detail, there are different sections in the draft that talk about, for example, first about connection admission. It mentions that SYN cookies are effective in mitigating SYN flood attacks, that services intended for use by anyone should be protected, or I'm sorry, not intended for use by the public should be protected with access controls. Specifically mentions this accept filter in the FreeBSD operating system. Applications must not be configured to refuse TCP queries that were not preceded by UDP. So getting back to that earlier point about it's allowed to use TCP first. And there's a couple of recommendations about fast open. So servers should enable fast open when possible. Clients should enable fast open when possible, and so on. So on connection management, there's quite a bit to say that, it says servers must actively manage their connections, to avoid resource exhaustion. Server software can provide limits on the total number of established connections, and as an operator, it's sort of your job to make sure that those limits are appropriate. Server software may provide a limit on the number of connections per source IP address or per subnet. The software should provide a configurable timeout for idle connections, and that clients and servers should signal their timeouts with the eDNS TCP Keep Alive option, which is an RFC. The software may provide limits on the number of transactions per connection and may provide limits on the total duration of a TCP connection. And it has a little bit to say about terminating TCP connections. Importantly, it says that it's preferable for clients to initiate close of a TCP connection, But on systems where a lot of connections are observed in the time-wait state, it may be beneficial to tune the local TCP parameters to keep that sort of manageable. And in extreme cases, it may be necessary to use the SO linger option with a value of 0 to prevent those connections accumulating. And a few last miscellaneous points. The recommendations in this draft apply equally to DNS over TLS, which is RFC 7858, as they do to just DNS over TCP. This draft does not make any references to DNS over HTTPS, at this time at least. And a few points about logging and monitoring that implementers need to be aware of, that TCP makes this a little bit harder. Don't ignore things like connection reuse and pipelining and out-of-order responses and so on. And that's basically the rundown of the draft. Happy to take any questions if you have any, or suggestions.
Is there any study or large-scale measurement on how prevalent is server-side support for DNS over TCP? Are you aware of any?
You're asking if there's any studies about the current levels of use of DNS over TCP? There probably are. I know that, so I was a co-author on the DNS over TLS document, and associated with that there was a study sort of theorizing how, what it would look like if there was a lot more DNS over TLS, and I think as a part of that there may be some background on what are the current levels of DNS over TLS. I can tell you for that some of the systems that that I get to interact with, it's on the order of 1 to 2% of the total traffic is coming in over TCP versus UDP.
Follow-up question. So you said there was a recommendation that the implementation may choose to use TCP first. Is there any sort of recommendation about some algorithm similar to Happy Eyeballs where DNS queries could be raised over UDP and TCP?
No, there's no recommendation specifically about that. It just says that it's it's up to the client's choice. It doesn't mention Happy Eyeballs by name, but I think certainly the expectation is that if you're doing DNS over TCP and if you have that connection already set up, then it makes sense to reuse that connection rather than say go back to UDP or something.
Got it. Thank you.
Tommy Polly, Apple. So thanks for doing this. I think this is a useful thing to encourage people to do and support more. So that's nice to see. Just 2 comments. One, so I'm glad that you're saying that the servers should support TFO. I'm a little bit more concerned about saying that all the DNS clients should do TFO. It may be good to soften that to a may, just because there are some issues with deployment, and this is oftentimes for clients a rare enough case that they actually are using TCP that if we're doing TFO in those cases, it may not get tested as much, and they may not notice the edge cases until they break in certain deployments.
Okay. So at this time, you would suggest a may instead of a should for that, but in the future, things might get better. And
right. Hopefully, yes, things will all be rosy, and maybe we'll hear more from Praveen. And so that was my comment there. The other comment was it was surprising to me how much the DNS over TLS references were kind of buried near the end. It may be good to just say that up front, such that it's very obvious from the intro of the abstract that this applies across the board, because I think as people are looking towards going to DNS over TLS, they should be aware that they should take these things into account.
Okay, yeah, thank you.
Regarding the TFO problems, I think the trend seems to be that the operating systems are building in fallback mechanisms. So the app should ideally be unaware of or be able to use the API freely without having to worry about. So even if we recommend should, I think there should be a caveat. They're saying there are known issues with TFO which are being resolved. So some experimentation should be done before rolling out the change.
So it may be worth adding some text specifically saying that, clients should feel comfortable enabling TFO because operating systems should.
Yes, so
Fallback?
yes, but
No.
we should add a caveat there saying that it should be, they should measure before they roll out the change.
Who should measure? The
The-
application should measure?
Yes.
Is that something the application can measure?
When I say application, I mean the DNS resolver, which could be wherever, it could be in the browser or the operating system.
Okay.
Jana Iyengar, I'll push back against that gently to say that, yeah, don't say should. It's not because I don't think applications can measure it. I just don't think that the people who are building resolvers have the expertise to understand the failure modes of TCP fast open. They're very subtle, and you know, we are discussing them, trying to figure out how to work around those, and you know, hopefully sooner than later they will be part of the default behavior in Apple, macOS, and Linux and Windows. When that happens, it'll naturally be available. So you might say, where available in the underlying platform, clients should use it or may use it.
So
I'd say may, not should.
you would advocate for May at this time?
Absolutely.
Thank you.
Okay, so thanks a lot for this presentation. So obviously this is not a TCPM working group document, but we thought it would be useful to discuss it here. And I think you also got some useful feedback.
Thank you.
So thanks a lot. And with that, we would move forward to the next talk. That is also not about a TCPM working group document. So please, Praveen.
This continues kind of the series of talks I've been doing about what we're doing with improving TCP in the Windows networking stack, work done with others. So this is a quick recap of all the advancement we have recently done. The good news is that all these improvements are now on about 800 million plus machines. So TCP is evolving on the internet. So IW10 was made the default for all TCP connections. The current loss recovery mechanism is RAC, which I will touch upon later in this talk. So RAC plus tail loss probe. Cubic congestion control is now default on all these systems for all outgoing connections. TCP fast open is enabled for limited websites on the Edge browser with aggressive fallback. It's still, there are still mailbox issues, so the operating system API internally has logic to fall back the connection to regular TCP if there are any problems experienced with TFO. If you are interested in the details of that algorithm, I've done a previous talk in TCPM which has the algorithm. LEDBAT++ is a new congestion control which I also presented in ICCRG, I think 3 IETFs back. This is also enabled only for limited scenarios currently. Any kind of background transfers like crash dump uploads or Windows updates. The delay attack timeout was reduced to 40 milliseconds. Traditionally, it used to be 200 milliseconds. This puts Windows on par with what Linux is doing. This, I think, over the long term will help a lot because currently the tail loss probe algorithm requires you to account for the worst case delay attack timeout, which is 200 milliseconds. In time, we hope that we'll be able to reduce that to 40. The Windows implementation always followed appropriate byte counting, so because it does not do pacing, the limit was 4 MSS worth of congestion window growth per rack. That has been increased to 8. On the server side, we have rolled out Cubic and TFO for all the Microsoft Online services. So this is again much easier to roll out on the server side. So that is currently supported on the internet.
Jana Iyengar, I meant to ask you this earlier, but when did you change from Compound to Cubic?
That happened about, I think, a year and a half back, and now it's default for all outbound connections.
Do you have any data comparing the two? Like, you know, did you ever talk about why it is that you chose to go to Cubic?
Yes, so I actually talked about that previously, but to recap, what the problem was that Compound was very delay sensitive, and we were finding that especially in the virtualized environment, because there is another set of hops that you go through on the host, there are a lot of latency fluctuations that would throw off Compound and have it react very negatively to increase delay. And we found that Cubic performs better. We understand that Compound was more well behaved in terms of buffer bloat because it would back off when there was latency increase. But in terms of raw performance, especially when you're, let's say, copying large files across two regions, Cubic would consistently win. Of course, there is increased latency, but in terms of throughput, Cubic did better.
Thank you.
So we have improved how slow start works in Windows, starting with hybrid slow start. So previously, when timestamps were disabled, which is the default configuration of the Windows network stack, the network stack was only collecting one RTT sample per round. But for high start to be implemented effectively, we made a change to collect more RTT samples per round. This has a little bit of performance overhead, but this was necessary for us to be able to implement high start. The portion of high start with that we chose to implement was the delay increase algorithm. The inter-packet arrival algorithm, when we experimented with it, was not behaving as expected because of LRO, as well as the fact that Windows has always done stretch hacking. I have put in the parameters that we're using. They're very similar to what was in the paper. But we found that high start actually exits prematurely. So especially when testing over Wi-Fi links or when there's congestion in the network, high start would exit very quickly, leaving us at a very small congestion window and immediately entering congestion avoidance. So we implemented limited slow start immediately after high start ends. So what limited slow start is a less aggressive form of slow start. It comes from RFC 3742. But that RFC talked about doing limited slow start right from the start. So what it defined was a max SS thresh parameter. And the recommendation there was like 100, the value of 100 MSS. But what we are doing here is that if we do exit slow start too early, we are doing limited slow start, because then the congestion window ramp remains at least a little bit more aggressive than what you would have in congestion avoidance. We tested this and we find this to work the best amongst all the various experiments we did for modifying slow start. We did choose to modify a parameter from that RFC. So the K value was computed using 0.5, which means that at most MSS by 2 growth per ACK. We modified that to 0.25, so at most MSS by 4 ACK, growth per ACK. These two algorithms are currently only limited to the initial slow start. We don't do this after timeout because we believe that we would have already found a good SS thresh value when we previously probed the network.
Should I just wait until the end?
If the question is about this, you can go ahead and ask.
Okay. This is super interesting. I believe that Linux actually does half, but somebody else has to verify that. But did you find that just leaving it at regular slow start after you exit, what happened when you did that?
No. So at the end of high start, we enter congestion awareness immediately, right? So of course. So that problem is then if we exit too early, like the min cap there is like 16 MSS is the SS thresh cap in high start. So if the value is higher than that, you could exit very early, and then you could have ample capacity. And just because of congestion, you exited too early, and then we find that limited slow start allows you to catch up. It's not as good as fast as slow start, but it's still better.
Oh, I see. So you're leaving the interpacket arrival there. Did you remove the interpacket?
Yeah, the interpacket arrival is not implemented. It's only delay increase. So you spot delay increase, you exit slow start, you enter congestion avoidance.
Got it.
But you might have exited too early.
Got it. So you're doing high start with only delay, and then you're doing limited slow start, and then
because we could have done wrong. We could have exited incorrectly, and then we're making up for that using LSS, and LSS is less aggressive. We find that it doesn't cause timeouts. So the regular slow start without high start would just cause timeouts.
I see. But LSS will keep going up until there's loss as usual.
Yes, but the advantage is that we find that with LSS, it's not a timeout. With do-pack-based recovery just works.
Got it. I see. Presumably the loss rate also goes down with LSS. That's probably natural. Okay, thank you.
Just to clarify though, that all of this is done without pacing. So we have not done any measurements on how this would behave with pacing.
Did you do any measurements in the wild, or is this lab measurements?
These measurements were done in the lab, and then we collected data about timeouts after slow start. And yeah,
Got it.
so things are better now.
Thank you.
Next slide. So RAC, currently the implementation is compliant with RAC, which means it follows pretty much all the recommendations in that draft. This is done in conjunction with the traditional packet-based measurement, which was the 3 DUPAC threshold. So that portion of the loss detection logic has not been removed. There are some portions of the RFC that are not yet implemented. So there is a DSAC-based dynamic reorder window that the RFC recommends, which is not implemented. There's also a reordering setting timer that can be used, which we are not currently doing. There's an optimization to be able to sort the sent packets in time order. The reason we don't do this yet is because we don't currently have the ability to retransmit loss retransmits. And if you want to do that, then the RFC recommends that you keep a list sorted in time order. So these are 2 optimizations we're looking forward to do next, but it's currently not implemented. Unfortunately, the draft status seems to be expired. So my request to the authors and the working group would be to move this draft forward, because this has pretty broad implementation and deployment at this point. And I think it's a very fundamental and important RFC that should be published as standards track.
Hey, Hiren, quick question. How does RAC and 3DUPAC work together?
They are both complementary mechanisms. You can leave both in place. So as long as 3 DUPACs, you could get like SAC information that tells you that there is more than 3 degree of reordering.
Right. My question was, how are you using that right now? As in, which one comes first, or if both are enabled? If what detects loss?
So the packet-based one automatically happens when you receive SAC information from the network. So it will immediately enter loss recovery if the loop thresh is exceeded. In the time-based implementation, yes, we currently don't have a timer, but that is also triggered by SAC or ACK information, but you may not have crossed the loop thresh, for example.
Right. And do you do you have 3 DUPACs, or you have N DUPACs where you?
No, so there is no dynamic reordering. It's currently set as 3 DUPACs. The only data I have additionally is that we mistakenly loaded it to 2, and we found that it broke a bunch of networks. So clearly, people have sort of adapted themselves to what TCP has been doing.
Thanks.
I have a quick, speaking as chair, I have a quick question on the last comment in relation to the other points that you mentioned here. So are you fine with the exact wording of the text, or do you think that there are changes needed, for example, regarding the things that you decided not to implement?
So we had a bunch of feedback on the working group. I think there was one more set of feedback that came on the working group about the draft, and those were supposed to be fixed. It's unfortunate that it was not published, but I believe the changes were made in the private working copy or something. In terms of text, I do think that there probably need to be a little bit more work, but in terms of the algorithm, I think it looks good. Those things that are not implemented are specifically called out as may. So those are just optimizations, but all the shoulds are implemented.
Okay.
Hiren, have you looked at PRR?
Yeah, so we are currently looking at PRR to avoid the burst losses during RAG recovery.
Exactly. We have found that without pacing, that will help.
Yeah.
Felix Wanrank, University of Applied Sciences, Münster. Sorry. Since you're using both loss detection algorithms, do you have any statistic data when DUPAC is better than RAG?
Unfortunately, then it will have to be either or. Then we can do an A/B experiment, but currently it's just an addendum. I believe that the Linux stack has moved away from packet-based detection completely onto RAG, but I'm not completely sure. We would like to do that in the future, but currently we are keeping the loop mechanism. So sorry, I don't have data to say which one is better or whether removing the loop thresh causes any problems, because we haven't done that yet.
Thank you.
Randall Stewart, Netflix. I have an answer for him. in our implementation, I have noted that there are times that middle boxes allow the SAC to be negotiated but strip all SACs out. And so when that occurs, the dupacks are very useful. Not too often, very rare, but it does happen.
That's a great point, yeah. Next slide, please. So the initial RTO has traditionally was always at 3 seconds. And the synchronous retransmissions were capped at 2. So the total timeout for TCP would typically end up being 21 seconds. So we are now lowered the initial RTO to like 1 second by default, which is the RFC defined minimum. The total timeout is still kept at 21. So it ends up being more retransmissions, but this was done for app compat reasons. The other thing I would like to point out is that previously, well, this change has been done for a while, but previously, some of the options like window scaling would get removed when there were send retransmissions, but currently the only option that we remove if there are send retransmissions is TFO. The other thing I would like to say is that there's also an API for applications to set more aggressive timeout values if they so desire, and there is a global configuration as well.
Jana Iyengar. So yeah, this is great. I was actually going to ask you if you have any way to reduce it below 1 second. But have you done any experiments to see what happens when you do it below 1 second?
No. So there is a knob. There is both an API and a global knob to lower it below. I think we allow you to go down to like 300 milliseconds. But no, by default, we haven't done any experiments to lower it further.
The problem is that in an application, I can lower it, but I don't have any way of measuring whether that caused retransmissions or not.
That's a fair point, yeah. But in terms of the API, yeah, we are assuming that the application would do their testing before making such a change. From the operating system point of view, 1 second seems like the safe value. There is cases, for example, where if we had previous path RTT measurements, we could actually go lower because I mean, even if there is ECMP and even if you're taking different paths to the same destination, if we could have a ballpark value, like I mean, you could have a function of like 2x or 3x the max RTT you saw on the previous connection, but currently we don't implement that optimization.
Right. So just going back to the question, I appreciate that there's definitely value in exposing the knob to an application that might have information, but if I was to do an experiment with this, I wouldn't know how to do it on Windows because I would run the experiment and as an application, I couldn't actually gather information about the number of retransmissions that were sent.
Now you can because there is a TCP info socket option API, so you can actually gather statistics on the connection after the connection is done.
Awesome. Okay, that's useful. Thank you.
That's it. Any other questions?
Michael Abramson again. ECN support, what's your thinking there? I think it's still off by default, right? You can turn it on.
ECN on client is off by default. On server, it's been on by default for a while.
Okay.
So server for outbound connections, which is rare, but you could assume like intra-DC scenarios where servers are talking to each other, ECN is negotiated. But for clients, it's currently off.
Are you considering, what's your thinking on changing the default on the clients?
So currently we are trying to experiment with TFO. So that's the reason we have not moved forward with ECN. It's something we are interested in doing in the future, but currently because the network doesn't support, there's not a lot of like ECN marking actually happening on the network. So it's
being an operator, I have a hard time getting it turned on because people are saying nothing, nobody's using it. The second one is, I know, but Windows is still kind of a largish player in the area. The second thing, does this relate to the Xbox stack as well?
Yeah, so the same network stack runs everywhere, like Xbox, HoloLens, PCs, desktops, servers, everything.
Right. So the Xbox is basically a normal Windows client when it comes to the settings and the choice of TCP algorithms and all that. Okay. Thanks.
Okay. So thanks a lot for this talk. We are hearing your comment on the Rec 1. So the chairs will talk with the others on what to do, and you will hear from us. But thanks a lot for this very useful information.
Thank you.
And with that, we will stop talking about TCP and looking at an alien technology. But still, I mean, the charter of TCPM actually allows us to think from time to time about algorithms that are used elsewhere. And that's why we thought it's good to have Jana here talking about some of the algorithms used in QUIC. So.
No. Give access to that. I have no access, and apparently this is alien technology. So prepare yourselves, people. Just go back one slide. So this is a continuing series of discussing quick loss recovery. This feels super weird. Is there a pink box here? Am I supposed to be in a pink box?
Yeah.
Oh, okay, fine. Oh God. And we have a German for a chair too, so that helps. All right. So this is in a continuing series of discussing quick loss recovery in TCPM. And the hope here is to get more people in this community engaged in the recovery draft and the discussion of loss recovery in TCP. So this is, again, the intent here is to give you a sense for what's going on there. It's less to litigate the constants and various things here in this room. There's going to be significant discussion on the recovery draft, basically a 1-hour discussion tomorrow in the quick working group. So please show up there and litigate all of these points there, or file an issue. That's even better. I'm going to start off very quickly with a rundown of basically what quick is. Again, this is for those of you who've been hiding under a rock for the last 2 years. No, actually, this is for those of you who know about QUIC but don't know the details of what's going on in QUIC. So don't feel too bad if you find yourself being educated through these slides. So QUIC, the QUIC packet format itself is different than TCP. So it's important to sort of change your mode of thinking a little bit, which might lend credence to Michael's comment about, oh my God, it's 2 Michaels. I forgot that, about alien technology. So the first is QUIC has 2 types of headers. A QUIC packet has 2 types of headers. There's a long header and a short header. Next. The long header looks like this. It has many bits. And it has a version in it. It has connection IDs, connection ID lengths. I'm not going to go into the details here, but the high order bit is that this header is used during the handshake and handshake only. It's used for establishing a connection. After the handshake, next slide, the connection moves on to using the short header. And it's short because it is short. And it has only a few fields, and those are like, the lengths of those fields are negotiated during the handshake, and so this can be super short. So it's basically a way of only having information in the header that's required for the rest of the communication. I'm not going to talk about what part here is encrypted and what's not, because that's not relevant to our discussion here today. But moving along, what else is in the packet? Frames. If you've seen SCTP, think chunks, but say frames. Next slide. There's frames are of different types. Frames come in many different flavors, and each frame has its own set of fields. Next. And here are all the different frame types. Read them all. I will quiz you at the end. It's all right. You don't have to read them all. Just know these 2. Next slide. The ACK and the stream frame. You don't have to just know these 2. These 2 are most relevant, again, for our discussion today. There are many other frames. Again, understand that the way this works is, if you're familiar with SCTP, it's quite similar to that. But if you don't, it doesn't matter. The idea here is that most of the control information in the protocol is basically sent via these different types of frames. They're not all sent in the packet header. The packet header is merely a way to find the destination for the packet. The rest of it is basically inside of control frames. So the stream frame is the thing that actually carries application data. The ACK frame is the thing that carries acknowledgement information. We'll look at these in a little bit more detail. Next slide. So here's what a stream frame looks like. A quick connection, first off, just for context, a quick connection can have multiple streams. And every stream has a stream ID. loss recovery, congestion control, all of these things are aggregated across the entire bundle of the connection, meaning across all streams. But every stream has and within that, every stream has a stream ID, and within the stream ID, a particular frame, a stream frame, carries a piece of data within a stream ID, and that piece is identified by the offset within that stream. All right, so the stream ID, there's offset, the length is the length of that particular stream frame, and then there's stream data. Next. So here's an example of what a quick packet might look like. The header bit is 1. What type of header is this? Pop quiz. You all fail. Some of you pass. It's a short header. Remember I told you there are 2 types of headers? The first bit in there indicates what type of header this is. That bit being 1 means it's a short header. And then there are other bits in there which I'm not going to go into, but these are all again in the short header. But one thing you'll note there is there's a packet number. The packet number is basically, again, we'll talk about it in a moment, but the packet number is the thing that we use for the entire packet. Next slide. Within a packet, you may recall that there are different frames. In this example, there are 2 stream frames and 1 ACK frame. Why are there 2 stream frames, you may ask? Next slide. Let's say, for example, that here's a real example. The packet number is 56. The first stream frame is from stream ID 5. It has an offset of 1123 because that's a nice even number. And there's data, there's application data on stream ID 5. All right? But this packet can carry more streams than just 1. Next slide. As in this example, you can see that this packet carries not just data from stream ID 5, it also carries data from stream ID 8. This is lovely if you want to tie the fates of stream 5 and 8 together, but in general, you may not want to do that. That said, you can do this. So there are different stream frames in the same packet here, stream ID 8 and stream ID 5, and there's application data of both of these, and this is all in the same quick packet. So that's for stream frames. Next slide. And here's what an ACK frame looks like. So this is important a little bit if you want to understand the rest of what I'm going to talk about with loss recovery today. So pay attention to this just a little bit if you've not been paying attention so far. We have the largest acknowledged, and so the ACK frame has basically a few fields, right? It has the largest acknowledged frame, the largest acknowledged field, I'm sorry, and that basically indicates the highest packet number seen so far. Note that while your TCP brain, not your alien brain, your TCP brain might want to think of this as a cumulative ACK point, it is in fact not. This is not the highest packet number seen so far that has been received in sequence. This is merely the highest packet number seen so far. So this maps to the highest end, the farthest end of the farthest SAC block that you have received so far. This is the highest packet number I've seen so far. There may be gaps below this. Okay, it's an important switch to turn to change in your head a little bit. We also in Quick explicitly encode the ACK delay. This is basically encoding the time since the largest SAC was received. The idea here is to capture the amount of time that the receiver is sitting on an acknowledgement before sending it back. If you understand, one of the problems with RTT measurements in TCP is that we don't know how much of that time was spent at the receiver, which was delaying the acknowledgement before sending it back. And this basically encodes that directly into the ACK frame so that a sender can make a more accurate RTT estimate. It can remove receiver delays from it. And below that are ACK ranges, and this is basically the discontiguous ranges below the largest acknowledged, much like SAC blocks. All right? Is that good, everybody? Any questions? Anybody still paying attention? Again, the same 2 people. What is going on in this room? There's food up front, by the way. All right. Let's move on to the next slide. That's basically the ACK frame. And now we get to the fun part of this. This is your test. I'm not going to go into the details here, actually. But this is just showing you how a particular packetization, how a particular encoding of an ACK frame might look like. And these details are, you can look at the slides later to get a sense for exactly how this happens. But as long as you understand the different fields and things that we are putting in the ACK frame, that's adequate for our discussion today. So next slide. And there's an example of the same quick packet with a particular ACK frame in this particular example. Okay. So again, remember the largest ACK is the highest packet number I've seen so far. And that's about it. Next slide. Now this is another example. I'm going to move past this. Next slide. Next slide. And next slide. And now we get to the more interesting example of a loss. Let's assume that the packet we were just creating, packet 56, is in fact dropped in the network. Also, let's assume that stream 8 was reset. Why? Because it's possible. Quick allows you to reset streams. Remember I told you that streams are things within a connection? You can reset streams. So let's assume that stream 8 was reset, meaning that the application says, I do not care about the data on the stream anymore, to send it or to receive it in both directions. It's done. Kill it. And let's say the quick loss detection detects that packet 56 was lost. Okay? Meaning that through whatever mechanism, and we're going to talk about the mechanisms in a moment, 56 is marked as lost. And let's say that the last packet that I sent out was packet number 74. Okay, I've been sending packets out, 56 was sent, I sent out 71, 72, 73, 74, and then I detected 56 as lost. That's where we are. Stream 8 has also been cancelled. Next slide. So going back to looking at packet 56, there's the packet header. Should we retransmit everything here? Come on, speak up. I know it's post-lunch. No, say people. Nobody says yes. This is a room that knows what I'm about to show. Good. Should we? Bob, don't pick that up now. Stream ID 5, the first stream frame. Should we retransmit that? Yes, says somebody in the back. And it's Randall. Should we retransmit stream ID 8? Why not? Because it was reset. Excellent. You're all on the same page. Should we retransmit the ACK frame? Confusion. No, we don't need to. We may want to send a new ACK frame. We don't retransmit the same one. And you get brownie points, whoever this was. I don't know, it was, yeah, there we go. Okay, you get brownie points. You get a strawberry. And what do we do? So next slide. So we don't retransmit those things, and we send a retransmission in packet number 75, not 56, 75. It's not TCP, it's alien technology. So the point here is that we're sending a new packet with retransmitted information in it. We may not retransmit everything. We may in fact choose to not retransmit anything at all. If stream 5 was even cancelled, there's nothing to retransmit. We detected loss, but there's nothing to retransmit, right? And I can choose not to retransmit 5 right now either. We'll get to that in a second, but I hope this general gist is clear. Next slide. So loss recovery looks like this. The packet numbers in quick basically represent transmission order. This is basically the premise of Quick's loss recovery, right? So packet numbers represent transmission order. They do not, however, represent the order in which the receiver expects to receive them. This is a critical difference. Remember that in TCP, receive order and send order are basically the same. Delivery order and send order are basically the same sequence number. But here, that's not the case. So stream IDs and offsets within stream frames are what are used for delivery order, meaning that a receiving quick implementation will deliver data up to the application based on the stream ID and the stream offset. As long as the stream offset is in line with everything that is expected within that stream, that data can get delivered. This has nothing to do with the packet number. Packet numbers in Quick are simply monotonically increasing packet numbers. They do not occur again. This is in fact fundamental to the security of the protocol itself, but we won't go there. The point here is that packet number 56, once it's dropped, will not reappear within that connection. Okay, that's important. And finally, there's a caveat about multiple packet number spaces during connection setup, but I'm not going to go there. So packets are basically containers. They carry various things, various frames, and packets are simply containers. It's a really nice thing to be able to divorce that from the way that stream data is delivered, because for loss recovery, I really only care about packet, what's in the packet, because the unit of drop is a packet and the unit of ordering is a packet from my point of view, transmission ordering, and that's useful for me as a sender. Bear in mind, however, that retransmissions are not automatically high priority. As I said, stream 5 need not be retransmitted right now, even though I've detected it as lost. My stream priorities, which are application dependent, might dictate that stream 5 is the lowest priority thing right now, so don't use any connection bandwidth for sending stream 5 data as long as you have stream 10 data to send. So it's possible that I don't retransmit right now. So we also have to divorce what happens to the congestion window and to loss detection from what is in fact transmitted when loss is detected. This is different again from TCP. Okay, next slide. On generating ACK frames, we basically follow similar guidelines to TCP, except that constants are slightly different. There's a delay ACK timer that is currently recommended at 25 milliseconds, meaning that you ACK every other packet that's received. There is a bit of a ordering thing here, where if the received packet is not the largest received plus 1, then you ACK every packet. That's recommended again based on just standard TCP behavior. So there is an expectation of ordering here to some extent. But a receiver is also free to process more ACKs before sending more packets before sending an ACK. There's no strict requirement that it must send an ACK for every 2 packets that are received. This is to allow receivers and senders, in fact, as well, to experiment with this. In fact, there's an issue open on trying to figure out if we can't make this something that's negotiated between the sender and the receiver and made more dynamic. There's a question coming up. Yeah, go for it.
Eric Klein, 25 milliseconds is a fixed number, or is it actually a function of measurements of latency in that connection?
It's a fixed number in the draft. It's a delayed acknowledgement timer for 25 milliseconds.
Okay, so for high latency.
Sorry, what?
For a high latency connection or for a long path, that 25 millisecond timer might get just kicked all the time?
So yeah, no, 25 milliseconds, no, because 25 milliseconds is about how long of time, how much time passes between packets that are received. It's not so much about, this is, the delayed ACK timer, this is not the RTO timer, right? So yeah, it's more about interpacket arrival times.
Thanks.
Yeah. So now we get into the meat of this conversation, 15 minutes into this presentation, because that's when it all happens, right? Quick loss detection. I'm going to walk through sort of what current loss detection is. Now this has come through a number of changes to the draft, and if you show up tomorrow to the quick working group meeting, you'll hear Ian talk about what's changed in the past 4 months. And there's a fair amount of change that's happened over the past 4 months. What I'm going to describe here is the current state of the draft. Okay, this is draft 19. So the way quick loss detection works is at a high level, loss detection only happens when an ACK frame is received. Okay, that's a premise. This is an important premise, and you'll see why in a moment. Meaning that when we receive an ACK frame that newly acknowledges a packet, then we use 2 different kinds of thresholds, packet and time thresholds, to detect a packet that was sent previously as lost. The packet threshold means that if I see reordering of greater than or equal to 3 packets, this is the same as TCP's 3-do-pack thing. Basically, if I see a packet that is acknowledged that's 3 packets ahead of where this missing packet is, then we mark this packet as lost. Or the time threshold, this is similar to RAC again, where if I receive 1 packet ahead, at least 1 packet ahead of the packet I'm looking at, I'm considering, but enough time has passed since I sent the packet, and enough time here is this particular value, then I mark that packet as lost. Okay, so there's time-based and packet-based, packet threshold-based and time threshold-based loss detection, both of them operating at the same time. So that's how loss detection works. And when I say this is how loss detection works, you'll see that this is broader than how it's done in TCP in a moment. Next slide. When no acknowledgements are received, however, so that works well and fine as long as you're receiving acknowledgements. When an ACK is received, I can do loss detection. But what if no ACK is received? What we do is we set a timer called a probe timer, and when the probe timeout happens, you simply send packets out. You send 1 or 2 packets. That's what a sender does when the probe timer goes off. And the probe timer is set like so, and this must remind people of the RTO computation. That's exactly what this is. With one important difference, there's no min RTO. Please don't come to the mic and yell at me yet. There's no min RTO. There's no min RTO, but there is a max ACK delay. The max ACK delay is in fact what is sent to me by the peer as something where the peer says, the receiver says, this is the maximum amount of time by which I will delay an acknowledgement. And so the PTO includes that, but it removes the min RTO. This is very much in line sort of with the rationale for why min RTO was even there in the first place. But that's the proposal right now, and Gauri's going to yell at me.
No, Jana. Gauri's going to ask a nice question. What does the probe packet contain?
What's the what?
What does it contain when you send the probe packet? What do you put in the packet?
That's a good question. Oh, thank you. You didn't yell at me. That was nice. The probe packet can contain pretty much anything. We don't actually say if you have old data, you can send old data. If you don't have that, you can send new data. But we suggest that you send new data before going off to sending old data, because we don't quite know what's happened here. The point here is that PTO basically comes from, it's an extension of TLP. So think of it as a tail loss probe that just keeps happening again and again and again. That's one way of thinking about this. So the premise here is that a timeout does not mean packet loss. Again, as I said, packet loss is detected when an ACK is received. Until an ACK is received, we don't declare anything as lost. There's an exception, but that's an exception. It's not the common case. We do not declare anything as lost until we receive an ACK. The reason this is useful is because it allows us to not have to deal with spuriously marking things as lost when we actually do receive an ACK. So the idea here is when a timeout happens, we don't do anything to the congestion window. We don't do anything to anything at all. We just send out probe packets. And when an ACK comes back, we do the actual detection. 3 minutes left. Persistent congestion. So when do we actually collapse the congestion window? Because there is an RTO thing in TCP, right? So at some point, you need to infer that there's persistent congestion in the network. And the way we do that here, because in TCP, you don't wait for an ACK to collapse your rate. So in this case, the way we do that is when there's basically been no ACKs coming back and all packets are basically lost over a long enough period of time. We've not received any acknowledgements over a long enough period of time. Then we collapse the congestion window to the min C1. The long enough period of time is effectively defined just directly in terms of time, in terms of the amount of time it would have taken for an RTO to fire. Right. So the draft right now has this expression here, and the idea is with the default is 2, which means that this is what effectively would have happened if you had 2 tail loss probes followed by 1 RTO. That's the amount of time that's computed in this expression. And then we say if there's been no ACKs received, but data has been going out for this period of time, then you mark the connection as in persistent congestion and you collapse the congestion window. Next slide. I'm not going to go into the details of this, but that's the loss detection part. Next slide. There's a bunch of tooling. Next slide. There's active work that's happening on tooling, and there's a whole hour on this in TSV area to discuss tooling. This you can actually use to look at loss recovery behavior and so on in quick connections with quick implementations. So please come to that and watch this, and that's the end of my talk.
So going back to what should be sent in the probe. I think like the current rack draft recommends that if there is unsent new data and the window allows it, then you send new data. Otherwise you send the highest packet that you previously transmitted, like the most recent old data. I think that's the recommendation in the current
in the current recovery draft. Yeah.
In the rack draft, I'm saying we could have a similar strategy in Quick.
I think we have some text along that lines in the recovery draft as well. Basically, the same logic being that you send new data if you can, otherwise you send old data.
Right. And in the previous slide where the congestion window was collapsed, can you?
Yep. The persistent congestion one.
Yeah, one more slide
go
back.
further. Yep, that one. No. The next. Yeah, that one.
So this is not just collapse the Mince event. I just noted that we should probably say that we mark everything as lost that is outstanding, right?
Everything is marked as, sorry?
So everything that was outstanding is marked lost at this point.
I can't remember if that's the case. Is that actually done in the draft? Oh, that's right. It gets marked as lost because enough time has passed. Yeah. So that's an event that right. Yes.
So does Quick follow RAC, TLP, combined draft or not?
It doesn't actually follow those drafts. I mean, this has been the loss recovery mechanism in Quick for the good 3-4 years now. But what we need to do is basically look at those drafts and make sure that we don't have very different values for constants, and if we have differences, then we justify them at least.
All right, and you went into setting congestion window a little bit at the end of the talk. So that's a little different than detecting loss part. And I think setting congestion window would come into play by whatever congestion control is in control at that point in time. So right now, I think default is Neurino for cubic. Right. Is there any rationale?
No, I mean, so the interface in the draft is quite clear about loss detection versus congestion control, and the idea, yes, you're exactly right. This is why I call this persistent congestion. So you would basically call into BBR, for example, and say, the equivalent of a timeout happened. But the interface is quite pluggable, and there is an API in the draft if you want to use that implementation, but the mechanisms are quite divorced from each other, even as described in the draft. So it allows you to use other controllers.
Thanks.
Yeah, so we are running out of time. So thanks a lot for this talk. As Jana has mentioned, so the intention was to raise awareness and to get feedback from that community. And I'm sure that you will understand where in other working groups you can contribute if you have any further comments. And with that, we are unfortunately out of time, which means that we don't have enough time left for the last talk that we had on the agenda, if time permits. Maybe we can have the talk next time. And with that, I'd like to thank all of you for all the interesting discussions and contributions, and see you then next time in Montreal. Thanks.
See you.